Okay, so in the previous video, we saw three operations on ideals. The sum of two ideals, the product of two ideals, and the intersection of two ideals. Now today we are going to see some examples involving these operations. So let's see this example 1 first. Here we have A. The ring A is the ring of integers, and in it we are considering two ideals. Because the ring of integers is a Euclidean ring, any ideal is a principal ideal. So they will be generated by single elements, single integers. I say is generated by the integer m and j is generated by n, where additionally we are also assuming that I and j are not both 0. One of them may be 0, but both of them are not 0. Then their HCF, highest common factor, or in other words their greatest common divisor, GCD, same thing, that exists, and that is a positive integer. What else do we know about this GCD? From number theory, we know that it's a linear combination of the given integers in this form. So for some integers lambda and mu, this h will be equal to lambda m plus mu n. What else? Because h divides both m and n. So m and n will be multiples of h. Say m is alpha h and n is beta h for some integers alpha and beta. Now what do we do with this h? It turns out that the sum of I and j is actually the principal ideal generated by that h. Let us see how. Suppose we take any element x in this sum. Okay, so what will x look like? X is the sum of some element of I and some element of j. Because I and j are these ideals, these elements will be multiples of m and multiple of m and multiple of n respectively. So accordingly, x becomes un plus vn for some integers u and v. Alright, now what we do next is that we use these expressions for m and n here. So that way x becomes u alpha h plus v beta h. We have replaced m with alpha h and n with beta h. And then when you take h common out, you get this x as a multiple of h. So that way x belongs to the ideal generated by h, and that is how I plus j is a subset of h. Then we need the reverse inclusion as well. So for that we take any element in this principal ideal. So that will be some multiple of h by some integer k, say we consider k. Now what we do, now we use this linear combination of m and n. So in place of h we write lambda m plus mu n. So that way you can see that the first term in this sum is a multiple of m, so it will belong to I, and the second term is a multiple of n, so it belongs to j, and that way their sum belongs to I plus j. So any element in this principal ideal is also in I plus j. So this principal ideal is also a subset of I plus j. Now you combine these two containments and that gives you equality. Okay, so that is one thing. Now next, what can you say about the intersection of I and j? That is coming next. So next, this is the intersection of I and j. We need an additional condition here. Now we need not just at least one of m or n to be non-zero, but we need both of them to be non-zero. Under that condition, their LCM exists. For considering LCM, for its existence, both the integers need to be non-zero. They may be negative, but both of them need to be non-zero. So let's call that LCM j. Now the LCM is divisible by both of them, so the LCM is a multiple of both of them. So say j is ym and at the same time zn for some integers y and z. Alright. Now the claim is this, that the intersection of I and j will be the principal ideal generated by this j, the LCM of m and n. Let's see how. Say you take any element x in I intersection j, then obviously since x belongs to both I as well as j, it will be a multiple of both m as well as n. So m and n will both divide x. In other words, x is a common multiple of m and n. So by the property, or in fact this is also another definition of LCM, the least common multiple will divide this any common multiple x. So j divides x, or in other words x is a multiple of j, but that makes x an element of this principal ideal. So any element in this intersection is here, and that's why the intersection is a subset of this principal ideal. Going in the other direction, say we take any element in this principal ideal, say w, then w is some integer multiple of j, say gamma times j for some integer gamma. Now you use these things here. In one hand, w is gamma times ym because j is ym. In the other hand, it is also gamma times zn because j is simultaneously zn also. So you see that w is a multiple of both m as well as n, and that's why w belongs to both I and j, and so it belongs to their intersection. So that way any element here is also in the intersection, which gives us this inclusion. So now you just combine this one and this one to get the claim. Okay, and finally we have the product of I and j. Okay, so next we have the product ij, and the claim is that ij is equal to the principal ideal generated by the product mn of the integers m and n. So let us first prove this containment, that ij is contained in this principal ideal. So we take a general element of ij. That element is going to look like this from the definition of ij. So what is this element? It's a sum of finitely many products. Each product is a product of two terms, one coming from I and the other one coming from j. Accordingly, we have taken some finitely many elements in I. That's how we started the argument, and an equal number of elements in j. But before we use them to consider this element, let us see what the consequence of them being in these ideals is. Since I is the principal ideal generated by m, each ai will be a multiple of m by some integer alpha I. Similarly, j is the principal ideal generated by n, so each bi will be a multiple of n by some integer, say beta I. Okay, and then we consider this element, in which if you use these things, you then get mn in each term, which you can take common out, and that clearly shows you that this is an integer multiple of the integer mn. So it belongs to this principal ideal, and that way you get ij as a subset of mn. Conversely, you take any element, say L, in this principal ideal, so it will then be an integer multiple of mn, say some delta times mn, where delta is some integer. Now you can note that this L can be considered as delta m times n, where delta m belongs to I because it's the multiple of m, and n belongs to j, well, that is also a multiple of n. And that's how this single product is also a sum like that, in which there is only one term, and that is why this element, which is L, is an element of ij. So that way any element of mn is also in ij. So we have this containment, and that's how we have our claim. Okay, so that is example 1. Next we see example 2, in which we consider the multivariate polynomial ring. So this is example 2. In this case, our ring A is this ring. In this n indeterminates or n unknowns, we are considering the ring of all polynomials where the coefficients are coming from a field K. And the ideal that we are, in this case we will consider only one ideal and we will see what can be said about its power. The ideal is this, which is the ideal generated by these monomials x1, x2 up to xn. And the claim is this: for any non-negative integer m, the mth power of I consists of all the polynomials in this ring where there is no term of degree less than m. How can we prove this claim? Let's see. Okay, so this is the proof. In the proof, we formulate a way of referring to that set, the set of all polynomials in which the terms have degree at least n. But it's a little bit more technical than that. So for any non-negative integer m, let Sm be the set of all polynomials f in A. A means our original multivariate polynomial ring, such that either f is 0 or f is non-zero and each non-zero term of f has degree at least m. Okay. So with this set now, our claim translates into this statement. So we want to prove that the ith power of that ideal I is equal to Sm. And we are going to use induction to prove this. Let us first note what happens when m is equal to 0. You may remember that we have defined the 0th power of any ideal in a ring to be the entire ring itself. So that is definition. So the fact that this is equal to A comes from definition. However, it is also equal to S0. Why? Because S0 actually consists of all polynomials, since the degree of any term by definition is greater than or equal to 0. So every polynomial will satisfy this condition when m is 0, and that is why S0 is A. So in this case at least, yes, the claim is true. Next, you assume the induction hypothesis. Say you assume that the claim is true for some non-negative integer m. And then you consider the m plus 1th power of I, which by definition is I to the power m times I. Now this is the product of two ideals. One of them is I to the power m, the other one is I. So how will the general element look? The general element will be a sum of products. You know that's what happens in the product of two ideals. So the elements will look like this: a1 b1 plus a2 b2 up to ak bk, where k is some positive integer and each ai comes from I to the power m, the first ideal, and each bi comes from the second ideal, which is I. However, what is I? The original ideal I is the ideal generated by those xi's, the unknowns. So the general element in I will look like this. It's a linear combination of those xi's, all the xi's, and the coefficients are arbitrary polynomials from the original ring. And you can clearly see with that because of this, there will be no constant term in any polynomial which is an element of I. There is no possibility for having any constant term in this type of sum, and that is why the degree of every non-zero term in a non-zero element of I must be at least 1. But then what can you say if that is the case? Then what can you say about elements of this form? Obviously, all the non-zero elements will have all the non-zero terms having degree at least m plus 1. At least m degree elements are these ai's, and at least 1 degree elements are these bi's. So when you multiply them, the degrees will be at least m plus 1, and that's how you get I m plus 1 equal to Sm plus 1. But then by induction, then your claim follows. So that's how you get this claim proved. After this, there are other things also, so that we will discuss in the next video. So that will be all for tonight. So see you tomorrow with a new upload. Until then, this is me, Lucifer from A Mathematical Group. Have a nice day.